Well, this talk is mostly about the Pandas project, but about Python data wrangling in general. And I gather that some of the people in the room do a little bit of data wrangling. I now work for 2 Sigma. I moved to New York just a couple of months ago under the radar, and so you know, mandatory disclaimer. So most people know me as having worked on Pandas, which is getting to be almost a 10-year-old project. It had its 8th birthday earlier this year. It's been open source for the majority of that time, but it did start as a closed source project in finance. Last couple of years, I've gotten involved in the Apache software ecosystem, and I'm now very involved in the Apache Arrow and Apache Parquet projects, and working on analysis tools here in New York at 2 Sigma. I spent the last couple of years at Cloudera working on figuring out how to bring the Python ecosystem and the Hadoop and Spark ecosystems together, which has turned out to be quite a rabbit hole of infrastructure problems that need solving, and I'll touch on those briefly. If you want to hear about some of those in much more gory detail, you should definitely go to Julien Ledem's talk later this afternoon about Apache Arrow. I started another project there called IBIS, which is an attempt to bring a deferred expression system that looks and feels like Pandas but can interact with SQL systems, especially SQL on Hadoop. But you could also make it run on Spark or many different backends. So that's also an interesting project you could check out. I am working on a 2nd edition of my book. So if you own, how many people own the 1st edition? I have several copies. So the goal of the 2nd edition, given that the ecosystem has settled down a little bit, so I'm comfortable writing about certain topics which I wasn't comfortable writing about in 2012, things like stats models, scikit-learn, which were brand new projects back then. Pandas was also a brand new project in 2011, 2012, but I used the book as a tool to help me finish the project. So I would come to an empty section in the book and say, well, I've got to finish the code so that I can write about it. But things have changed a lot the last 5 years, and I'm sure many of you are well aware of that. So 5 years ago, Python had become accepted as a scientific computing language. The community was really focused on how do we get people to move from MATLAB to Python. That was the real consuming, like if you went to SciPy, anything related to NumPy, SciPy, the numerical analysis stack in Python, it was all about how can we get into the traditional academic-oriented scientific computing ecosystems. And that was things like MATLAB, but now data science has become a thing, and Python has become a primary language for data science, and it's really great to see companies like Google choosing Python as the language to make their next generation deep learning framework available to normal humans. So that's a big milestone for the community. And the fact that we have lots of conferences and places where you can go and meet other Python programmers, also go to learn about how to use these tools. SciPy conference has been around for a long time, but now we have PyData conferences, and there's Python tutorials at all of the Strata conferences. So there's many places you can go and be a part of the community. So the community grew for a number of reasons. It didn't, Pandas certainly helped, because data is very messy and we all have to clean up data. So if you don't have good data manipulation, data cleaning tools, then all of the rest of the things that you want to do become very difficult. So it was certainly an important part of the equation, but we needed all of these other things. We needed packaging. We needed to be able to reliably install the same packages that you have on your machine on your colleague's machine. So having Anaconda, having better binary wheels with pip made a big difference. Jupyter notebooks have obviously been huge. Scikit-learn has been huge. And all of it has been made possible by the foundation of numerical computing and NumPy and SciPy. Another very exciting thing that's happening right now is a project called Conda Forge, which if you're not aware of, I will make you aware of it, but it is a community-led initiative to build Conda packages. So if you have a library that you want to make available to Python programmers all around the world, they provide a hosted build infrastructure where you can put up your Conda package recipe and it will get built on an automated basis and deployed so that anyone can Conda install your package. And they've dealt with some of the really unpleasant things like, how do I ship this library even though I'm running Ubuntu 16.04, which has 2 new glibc and 2 new libstd C++, and so they've set up a compiler toolchain so that you can deploy on many different Linux distributions without running into weird ABI conflict issues. And so if you've done a lot of C or C++ development, this is what you end up spending a lot of your time dealing with. So they've solved that problem, so bravo, it's really fantastic. Another thing that I've been caring a lot more about as I've been doing open source for a longer amount of time is how do we fund open source? Because we all depend on open source heavily, and I'm sure that you and your companies, where would you be without all these open source projects? But it's very hard to collect money to fund their development. So people like me, I have chosen to work for companies specifically where I have the opportunity to do open source development. So I chose to be at Cloudera because that was a place where I could do open source development. Now being at 2 Sigma, 2 Sigma is a place where I can continue to do open source development. That's not always an option for everyone, and it would be great if we had better funding avenues to collect funds and enable people to work full-time building these projects that everyone relies on. So NumFocus is one organization which was originated in the Python community, but provides a way for companies to give money to open source projects where it goes into a not-for-profit organization, and then the owners of those projects can decide how to distribute the money, whether it's to freelancers or whatever. So if you have spare cash and would like to fund projects, I encourage you to look at NumFocus as one possible way to support the projects that you depend on every day. So most of this talk is about the Pandas project itself, and I will try not to put you to sleep with extreme technical detail, but just reflecting on the project structure, where we are, where we came from. We just released a few weeks ago the 0.19 release, and it's funny because the project is depended on by hundreds of thousands of people around the world, that it's still not a 1.0 release, that we're in this eternal beta mode. But the biggest thing that's happened in the last 4 or 5 years is the contributor base has exploded. So if you watch the project on GitHub, there's an extraordinary amount of activity. We've had over 5,000 pull requests, and that's all since we joined GitHub in 2010. So that's multiple pull requests per day, every day for 6 years, which is crazy. The amount of issues that have been created, a lot of those are feature requests. Many are documentation, bug fixes. Some of the number of pull requests and the number of issues are also because the Pandas project has grown into this sort of super library that's trying to solve every problem under the sun related to data manipulation. And that's good because you have something that's full stack. It's a one-stop shop for solving lots of different problems, but it also makes for huge amounts of edge cases and different little bugs that creep up. And the fact that there's only 11 developers who have more than 100 commits on the project will show you that a lot of the contributions are coming from real users of the project who are just using Pandas to get their job done, and they run into a bug and they fix it, and then they become a contributor to the project. So if you look at the Google Analytics just for the Pandas website, it's been steady up and to the right for the last 5 years. I don't really know how big the user base is, but we have maybe 70,000 unique visitors to the website every month. So it's probably somewhere in the low hundreds of thousands of users worldwide. There's certain lessons you can learn if you're working on another open source project about how to make open source projects successful. I would say one of the biggest reasons that Pandas has grown so big and become so successful is because the contributors are extremely active. So if you're run into a bug, you write a patch, the worst thing that can happen when you want to be involved in an open source project is you submit a pull request on GitHub, and then it sits there. And so it's crickets chirping for a week or two, and you pester the contributors, and maybe they review your code. But in many cases, if you submit a patch to Pandas, it will get reviewed the same day, feedback requested, and you could have less than 24-hour turnaround time to get a patch merged into the project. Of course, the library has lots of other benefits. The fact that its performance is good, that it's one of the only data preparation, data cleaning tools in Python available. Since you have dirty data, you want to program in Python, so Pandas is the tool that you use. That has helped attract a lot of people to the project. And the fact that it's been used continuously in production over its entire lifetime. I think we first used Pandas in a production use case in May 2008, and so that was probably a bit premature given the primordial state of the library at that time, but we survived. So with an 8-year-old project and over 200,000 lines of code and hundreds of contributors and hundreds of thousands of users, the risk is that you get into this paralysis mode where you can't change anything because it will upset too many people, but yet you have technical debt because there were architectural decisions that you made early on which made sense then and maybe don't make sense now, or about new use cases which you didn't know about 5 or 6 years ago that are now popular use cases for the project. Like we didn't really think about people using Pandas for database ETL. And so maybe many people in the room use Pandas for ETL, and that was not something that we thought a lot about. Another interesting trend is that Pandas is being used as a component in larger systems. So people are using PySpark as a way to orchestrate small Pandas jobs. So run this map function, which uses Pandas to transform some data, and then run this reduce function, which uses Pandas to combine together data sets. So any problems that were related to that distributed, partition the data set, run all of these independent Pandas functions, and then merge together the results, has brought up a number of engineering challenges to make that more flexible and more performant. So one concrete thing that we're going to do, which you should look out for, is that we are finally going to release Pandas 1.0, which is probably long overdue. It won't be majorly different. We're not going to break a bunch of things, but we are looking at what are the last API changes we want to make before we say that the library is API stable, let's focus on stability, let's just fix bugs, make the library faster, make the documentation better, and stop changing arguments or breaking APIs. And if you go over the last several years of the project, we've broken a lot of APIs, but almost all of them have been good breaks. And so if you look at any API change in isolation, you can say, oh, it makes sense why you changed this. But if you're upgrading, sometimes people will wait 3 or 4 major versions of Pandas to upgrade, and all of a sudden you're dealing with a cumulative set of 100 API changes, and you haven't written enough unit tests, and so you have a really difficult time upgrading your code base. So we would like to stop that pain for a while so that we can take a step back and look at the technical debt that is accumulated in the project. So if you use Pandas heavily, especially for ETL, maybe some of these problems are well known to you. You can't have missing data and integers and Boolean columns, so it's not uncommon to read data from a database and find that the data types have changed, and they've changed without telling you. And that's not very nice, because when you go to write the data back to the database, you've got to say, oh, well, this column was originally an integer, but now it's a float with nans. And so you've got to have a bunch of ad hoc massaging code to fix the schema of the implicit schema of the data frame before you write the data back into the database. And so that's something that we would really like to fix. Another issue, which has as the data has gotten bigger, and I think we can all agree that data sets 6 or 7 years ago were a lot smaller than they are now. Pandas is a fantastic tool if you have 100 megabytes of data or a gigabyte of data. But if you have 10 gigabytes of data, 20 gigabytes of data, you start to spend a lot more time worrying about, well, is this line of code that I write going to cause the memory to double? And there are a lot of places in Pandas where you can accidentally cause memory doubling. And so that's not great. There are certain places where there's unavoidable data copying. Because of Pandas' relationship with NumPy, NumPy allows you to mutate any array. I mean, there is a flag you can set to disallow mutation, but it's fairly easy to accidentally mutate another data frame's data. Like if you slice a chunk out of the middle, you change that chunk, it's reflected in the parent. And that can cause very unintuitive behavior. If you're writing a big group by, you mutate a chunk of data inside the group by, and you find the original data set has been destroyed. And that's a very common stumbling block for users of the project. So that's one thing that we can fix. It won't be easy. One solution to it is to make all views in Pandas copy-on-write. So if you obtain a view on a data frame, it will be 0 copy, so it won't copy any memory. But if you mutate that view, at that point it will copy the memory so that the parent's memory is protected, and vice versa. So if you have a child which has sliced, let's say you load a giant CSV file and you slice out a portion, and you mutate the parent in some other code, you don't want the child's data to be mutated. So the copy-on-write goes both ways. Another issue for performance, and with our friend Moore's law, the CPU cores aren't getting any faster anymore. There's just more of them, and unfortunately, a lot of Pandas is very single-threaded. Some of the single threading is hard to deal with because it's also mixed up with the Python global interpreter lock. So whenever you're working with strings in Pandas and you want to access the data that's inside a string object, you have to acquire the GIL. So this is a problem if you have a large amount of text data or string data and you want to process it in parallel, because those threads have to acquire the GIL every time they either create a string or they want to access the internals of the string data structure. So, certain things we can do there, like moving all of the data in Pandas for common types like strings. I don't know, we don't really use the term off heap in Python, but you can think of it as moving all of the data outside of Python objects into an area of memory where we don't have to deal with the Python global interpreter lock, is one way around that. So the last big thing is, if you're a Spark user, you're a Dask user, we'd like to make Pandas work a lot better with those systems, a lot faster serialization, moving data around, and tools to make these more distributed MapReduce type algorithms easier to write using Pandas as a building block. So the summary of all this is that for the last year or so, I think since last December, we've just been discussing a project we're now calling Pandas 2.0, which is a significant re-architecting of the internals of the Pandas project. And the hope for Pandas 2.0 is that you as a user won't know about it. You'll need to learn some new semantics around if you have code which assumes that you can slice a data frame and modify it and it will be reflected in the parent. So things like modifying views, the semantics there will change because of the issues that I've just talked about. But for most Pandas users, they'll just continue to use the library as they have. Their code won't have to change. So hopefully we can get to 95% backwards compatibility, 98% backwards compatibility. But we won't be able to have 100% backwards compatibility because some things do need to change. Things like missing data. We want to have missing data in integer columns or Boolean columns, and you can think of that as an API change, and that will cause backwards incompatibilities. But these are just things that we need if we want Pandas to be a serious tool for data engineering. We can obviously make the performance a lot better. Some of that will come through multi-threading, more careful memory management. But over time, with these big multi-core machines with lots of RAM, we need to be able to fully utilize the hardware that we have, rather than assuming that everything is single-threaded and that we don't have very large data sets. So I don't know if anyone is a C++ programmer in the room, but one of the big components of the project, if you look at how Pandas is implemented internally, so in 2008, when I started building the project, Pandas was all Python. So there was no C, there was no C extensions, anything like that. It was all Python, and and that was fine for a while. It was fine for several months until you start profiling and you find a few hotspots and say, okay, I'm going to write a few C extensions to make those hotspots faster. So fast forward 8 years later, and now we've got an extremely large pure Python core business logic of how series works, how data frame works, and hundreds of C extensions. And it's all been organically driven, grown incrementally, without a lot of thought about a bigger kind of system architecture. Most of the C extensions are not very interrelated either. So a big part of the project will be refactoring from this structure of a big Python core, pure Python core, which is relatively slow, into a very tight C++ core, which we're going to call libpandas, and that will be wrapped in Python, and that will be where the user interface that you see lives. So I'm not going to go too far down in the weeds, but if you're really interested, we can talk about some more of some of the benefits of the new architecture if you want to get involved in the project. But this will give us a lot more flexibility to handle some of these memory management and low-level data representation issues, things like missing data. It will also make some of the cheap operations in Pandas, like selecting elements, selecting columns. You might have noticed that some of these indexing operations over time have gotten slower, so we want to make those a lot faster again. So if something can take less than a microsecond, let's let it take less than a microsecond. Another thing that is a big deal for working with really large data sets and has been a long-standing issue is that if you have data on disk, there's no way to, there's almost no way to memory map that data and make it look like a data frame. So you have to completely load the data into memory. And so there's a linear cost to making data available to Pandas based on the size of the data set. So if you have 10 gigs of data, you've got to load all 10 gigs into memory. 50 gigs, same deal. If you have a very large data set, maybe it's got 1,000 columns, it's 100 gigabytes, but you only need 10 or 20 of those columns. It's hard to say, only load those 20 columns depending on how you've stored the data. So we'd like to make that kind of lazy loading of columns as you need them a lot easier. There's been a lot of work with file formats, so there's a lot of work that we can look at there, or at least planning to integrate with some of these on-disk file formats. And this aspect will be critical to making Pandas a lot faster as a tool that's used with distributed applications like Spark and Dask, so that a Spark worker or a Dask worker can receive a payload of data, can memory map that rather than having to go through an expensive deserialization process to produce a Pandas data frame. So all of this is very closely related to a project that I've been a part of for the last year or so called Apache Arrow, which we just released as a new open source project. I'm not going to go much into detail. You can learn more about Arrow from Julian later. But this gives us in-memory data structures for tabular data, so not unlike Pandas, and a protocol for moving data around between processes with minimal overhead. And so you can think about the Arrow problem of I want to move data from point A to point B. Ordinarily, you'd have to write a custom adapter between two sources. And in the new world, using Arrow, we can have a single interchange format that is very efficient to read and write. And hopefully that Pandas can memory map without having to do a lot of deserialization work. So a couple of places where we're already using this that I've been involved in. So earlier this year, I worked with Hadley Wickham in the R community to create a project called Feather, which is a file format for storing data frames. So you can write a data frame from Python and read it in R, and it operates at roughly disk speed. So if you have a fast SSD in your hard drive, it's not uncommon to be able to read and write Pandas data frames at 1 to 2 gigabytes per second, which is pretty good. You still have the problem of having to load all of the data into memory, which will take some time to solve, but that's very nice. We're also working on adding native Parquet support to Python. So all year we've been building a brand new, from the ground up C++ implementation of Apache Parquet. And the target data structure for data coming from Parquet is arrow arrays, which can then be marshaled back and forth to Pandas data frames. And that's very fast as well. So just to give you an idea of the benefits of fast serialization and the impact that it can have on your analysis, so I did some back-of-the-envelope benchmarking, 1 gigabyte Pandas data frame, 100 columns, and I looked at a bunch of common serialization formats. And to be truly rigorous, I need to publish the code for the benchmarks so that you can run them yourself. I didn't end up adding everything to this benchmark, but so basically I used the Arrow has a interprocess communication format. We're calling it a file format, but it's not really a file format. Pandas has an interface to HDF5 called HDF store, which you may be familiar with. You can also pickle Pandas data frames. There's another library, Python-specific library called bcalls, which is another columnar file format, which you can read and write from Python. And these are all RAM to RAM conversions, so I wanted to eliminate the conflating factor of disk performance or network I/O performance. So this is just data in memory converting to a Pandas data frame. And so it's very promising that we can get in-memory bandwidth between one data structure representation and another that's over 6 gigabytes per second. But something I'll point out about these benchmarks is that in the case of Arrow, this 150 milliseconds is entirely in the Pandas data frame constructor because it insists on making a copy of all of the data that you're passing it. So in a world where everything is zero copy, you can receive a blob of data and memory map it without having to go through an extra copy step, this time effectively goes to 0. So you can think of it as being almost infinity times faster. So that will be very nice. And I see that happening in the future. It's just a matter of writing code. Famous last words, right? But just, to put it in context, comparing with another common serialization format like CSV files, we shouldn't complain too much because parsing CSV files can be quite slow. And even though Pandas read CSV is fairly fast, you're still looking at maybe, if I can do mental math, 40 to 100 something times slower to deal in CSV files. So a friend of mine, Damien Eads, wrote a library called Paratext, which uses multi-threading and a lot of C++ metaprogramming magic to get CSV parsing up into the bandwidth of these other serialization formats. But there you're really trading a lot of CPU time for CPU cycles to get performance out of CSV files. But sometimes you have data in CSV, and so you need to parse it as fast as possible. But if you think about these file formats, a lot of the file formats that we use in Python are proprietary. So pickle is a proprietary format. bcalls is proprietary. There's some other proprietary formats that you can use. And there's a lot of benefits to using a data format that is not Python specific and that other systems can read, especially systems in the Java ecosystem, which traditionally have had a really difficult time interacting with Python. You may have to interact with the JVM through shared memory or through sockets or some other means. You can do JNI. That is very painful, but you can do it. But that's a very exciting, possibility to bring, a lot tighter, a lot faster memory bandwidth between the Java ecosystem, especially Spark, and the Python kind of, Pandas, scikit-learn kind of ecosystem. You can also do things like, if it's a common data format and you can, pick out a column or pick out a set of columns, so you can start to think about predicate pushdown and filtering filtering on disk without having to first load the whole data set into memory and then filter it. So that can also give you a lot better performance in certain applications. We haven't planned, adding indexing on top of some of these formats, but that's something you could do to also improve I/O performance. But for the Python community, because there's a very small number of us writing code, to be able to benefit from the development efforts of other language communities means that they will do some of the work that we don't have to, and so kind of the rising tide lifts all boats, and that's so that would be very nice if that ends up happening. So I 30 minutes went by very quickly, but thanks to the DataEngConf organizers for having me here, and of course, none of this would be possible without my collaborators in the Pandas community, the core developers, and my collaborators in the ASF ecosystem. So thanks for listening, and we have 5 minutes for questions, maybe.
Are there any questions? Nope. Okay. There. So just
brains are full.
Oh, actually, hold up. There's one back here.
Just going back a few slides to you were talking about the big new features for Pandas 2.
Wait, this one or this one maybe? One of these.
One back. I'll just blurt it out. So as you add these bigger meatier features like support for external engines and more formats, just what separates Pandas from being a database engine at that point? Like in your head, what is the key difference in what it is?
Well, database engines are, I guess you have to define what is a database engine. So there's a can of worms. Do you have transactions? Do you have consistency? Consistency guarantees. Pandas has always been an in-memory single node analytical tool, and I don't think we intend to go beyond that. Obviously, single nodes have gotten bigger. They have more cores and more RAM. And so our goals with Pandas 2.0 are to better utilize, the hardware that's available on single nodes, and to leave the distributed computing problems to other systems, but let Pandas plug into those systems with less overhead. But as a database or a SQL engine, or using Pandas instead of Postgres or some other kind of SQL system, we have no plans for that. Possibly. You have systems like KDB, which, they are technically databases. So you could imagine if you had a way to, append, here's a Pandas data set on disk, and here's a way to write, write data to it. You could start to think about it like a database, but that also brings with it a lot of other expectations, like you write data to disk. You would like to be able to read that data in the future. So having backwards compatible file formats, it's kind of a rabbit hole that I'm not sure that we want to go down. But in a way, in-memory analytics, databases are not so far apart semantically. So it will be interesting to see how that does develop in the future.
I have a slightly unrelated question. Why do you think it is? It was the case that Python became the language that the scientific computing community decided to use, as opposed to, let's say Java was, would be an obvious choice.
Yeah, I think the biggest reason was in the late 90s, early 2000s, there were a lot of scientists and academics who spent a long time taking all the legacy Fortran, C, C++, computational libraries, and building Python interfaces for them. And I think the JVM, his biggest struggle has been numerical programming. So things like BLAST, LPAC, MKL. You can get at these things through JNI and off-heap memory, but it's still, even now, like, it's an active area of development and research. And so the fact that because of like architectural, like, just development challenges of doing numerics or linear algebra and like array computing in Java, I think there wasn't the activation energy. And in the late 90s, the Java development community was very much focused on building enterprise applications and not doing scientific computing. Also, Python's very nice to program in, so I think a lot of these individuals were attracted to Python out of laziness. It's like, oh, I can get done with less work. All we have to do is build nice user interfaces to the computational libraries, and so Python became a scripting layer for Fortran libraries and C and C++ libraries, and so kind of the orchestration layer for the high performance code. And that's still the way that Google and the scikit-learn, and it's the way everyone is approaching the problem. It's kind of the iceberg model of you see the tip of ice poking out of the water, but there's a big machine underneath that's unseen. And that's all the computational libraries, which are decades of development.
Do you think this is going to continue, or is Pandas 3 going to be in Julia?
Yeah, I mean, we could have Pandas in multiple languages. We'll create a brand. Sure, yeah.